When we have a dataset where one class is much more frequent than the other one, we have class imbalance. Our credit card fraud detection dataset has class imbalance because it has many examples of non-fraudulent transactions and only a few examples of fraudulent transactions. When we have class imbalance, types of errors play a very important role. In our credit card fraud detection example, we wanted to spot all the fraudulent transactions, and so minimizing false negatives was very important for us. Many real-world datasets have class imbalance. We have seen this example of credit card fraud detection dataset, which was highly imbalanced. Another common example is click-through prediction. These datasets are drastically imbalanced. For example, on the intranet, you are shown a number of ads, or on social media, you are recommended a number of people. You don't really click through all of them. So, in these datasets, we keep track of how many of these ads we click versus how many of these ads we do not click. And the ratio of click versus non-click is going to be highly imbalanced, because if you are shown like 100 or 200 ads, you only click on 1 or 2 ads. So the ratio is going to be, say, 99 examples of no clicks versus just 1 example of click. So these click-through datasets are usually highly imbalanced. Spam classification datasets are also imbalanced because we have many examples of non-spam versus only a few examples of spam. So far, we have been talking about different metrics to assess our model when we have class imbalance. But how do we actually address class imbalance? When you are dealing with a data set which has class imbalance, a very important question to ask yourself is, why do we have this class imbalance in this data set? Is it because of the nature of the problem we are dealing with? For example, if you are working on, say, fraud detection or click-through prediction, then that's going to be the nature of your problem. Usually, fraud transactions are going to be rare compared to non-fraud transactions, and clicks are going to be rare compared to non-clicks. If that's the case, and if certain kinds of errors are more important to you, for example, in fraud detection, we want to reduce false negatives. We want to be able to identify most of the fraud transactions. So, certain kinds of errors are important for us. If that's the case, we need to deal with class imbalance. We need to address class imbalance in this data set. Sometimes you have class imbalance because of the methods used in data collection. Data collection is not perfect, and if you have class imbalance because of data collection methods, then the distribution of classes in this collected data is not going to be reflective of the real-world distribution of the target. In this case, again, you need to address class imbalance, because if you don't do that, and if you deploy your system, then it's not really going to perform well on real-world data. Here I gave you 2 examples where it's important to address class imbalance. But sometimes you have class imbalance and it's okay to ignore it. Just that before making this decision, think about all these different aspects carefully. False positives and false negatives, they can have different real-world consequences. In precision recall curve and ROC curve, we saw that we can change these prediction thresholds and we can change number of false positives and false negatives. Then we can pick a threshold that's appropriate for our problem. For example, if we want high recall, then we can lower this threshold. So in our fraud detection example, we lowered the threshold to 0.1 so that we can catch more fraudulent examples. So this was our original classification report, and this is our classification report when we chose this threshold of 0.1. And with this threshold, now we are getting better recall compared to before. Now this is one way to address class imbalance. we are reducing false negatives by reducing or changing this threshold. Now, instead of changing the threshold, we can also change the model itself so that it takes into account the errors that are important to us. How can we do that? There are two common approaches for this. The first one is by changing the data, that is undersampling the data, oversampling the data so that we have balanced classes. And the second approach is changing this training procedure. Now, in this particular class, we are not really going to talk about this changing the data approach. We are only going to briefly talk about changing the training procedure approach. But I'll quickly tell you what's the idea behind changing the data approach. So the idea is that we have class imbalance and one class is more important for us than the other one. Then what can we do? How about reducing the number of examples of the most popular class? Like in our fraud, non-fraud example, we would reduce the number of non-fraud examples so that we have equal number of fraud and non-fraud examples. And the second approach is oversampling, which is how about increasing the number of fraudulent examples so that we have equal number of fraud and non-fraud examples. For example, if in our dataset for each fraud example, suppose we have 500 non-fraud examples, then what we want to do is we want to repeat that fraud example 500 times so that we have equal number of fraud and non-fraud examples. That is oversampling. This class weight approach is similar to oversampling approach. But in this approach, we don't really have to explicitly create or repeat these examples on our own. Scikit-learn does that for us in a smart way during fit. All scikit-learn classifiers have this parameter called class weight, which allows us to specify which class is more important for us. For example, here I'm showing you documentation of logistic regression. It has this parameter class weight. By default, it is none, and we can specify it using a dict or a string called balanced. How do we specify weights associated with different classes? We specify them in the form of class label :weight. Let's look at an example. Here I'm plotting our confusion matrix for X valid and Y valid on our fraud detection dataset. And these are the classes of our logistic regression classifier. So this 0 class corresponds to non-fraud and class 1 corresponds to fraud. Now, I'm specifying weights associated with each class. So I'm using this class weight parameter and I'm saying that I want to give a weight of 1 to class 0 and weight of 10 to class 1. So I want to give more weight to this class 1. That's what we are saying here. And with that now, this is our new confusion matrix. So with this new pipeline, we fit the pipeline and we are plotting the confusion matrix on the validation set with this new pipe LR underscore weight. And what do we see now? Now, compared to before, we have reduced our false negatives. Before we had 38 false negatives and now we only have 21 false negatives. So giving more weight to class 1 seems to have helped. But as a consequence, we can see that we have more false positives now. Before we had only 8 false positives, but now we have 27 false positives. Now let's try this class weight equal to balanced. What happens when you use class weight equal to balanced? Suppose in our fraud detection dataset, for every fraud example, we have 500 non-fraud examples. Then when we use this class weight equal to balanced, it's similar to saying that repeat this fraud example 500 times so that we have equal number of fraud and non-fraud examples. Again, we don't explicitly have to repeat these examples on our own. When we provide this string to scikit-learn, it's going to do that on its own in a smart way during fit. Okay, so let's try this string. And now this is our confusion matrix. So we are passing this class weight equal to balance string to our logistic regression. We are fitting this pipe LR balanced, and this is our confusion matrix on the validation set. With class weight equal to balanced, we managed to reduce false negatives further. We only have 11 false negatives now. Before we had 21 false negatives, but now we only have 11 false negatives. That said, we have many false positives now. We have 1,666 false positives. If you are using this system in a bank, for example, it is true that there is going to be a big cost associated with false negatives. You want to identify all fraud transactions. But there is also going to be some cost associated with false positives. If there are many false positives, then the bank will be calling many customers for fraud transactions which are not actually fraud transactions. So there is going to be some cost associated with it, and you don't want this number to be too big. So you kind of want to be careful that you are reducing false negatives, but you're not increasing false positives too much. Let's compare the results of logistic regression when we do not pass class weight equal to balanced versus when we do pass class weight equal to balanced. I'm going to compare these results using all these metrics: accuracy, F1 score, recall, precision, ROC, AUC, and average precision. And here are the results. Now what do we see here? When we use class weight equal to balanced, our recall is much better, but our precision has dropped a lot. So we need to compare it with the operating point. We need to make sure whether this is an acceptable precision or not. If it is acceptable precision, if recall is the only important thing, then we are okay with using class weight equal to balanced in this scenario. If not, if this precision is not acceptable, then we might want to optimize this class weight hyperparameter using different values for class weights and consider the class weight which gives us some acceptable value for precision. Usually when you use class weight equal to balanced, you will notice that your accuracy goes down. But that's okay. Accuracy is not something we are trying to optimize anymore. We care more about recall, and our recall is much better. So it's fine if our accuracy is going down. A similar idea of balancing classes can also be applied in data splits. You might be wondering about how does splitting work when we have data imbalance or class imbalance. In train test split, we have this argument, stratify argument. And by default, it splits the data so that if we have, say, 10% negative examples in our data set, then each split will also have 10% negative examples. And if we are carrying out cross-validation, by default, it also uses this stratified splitting. So in other words, if we have 10% negative examples in total, then each fold will also have 10% negative examples. Is stratifying a good idea? Well, when you use stratifying, it's no longer a random sample, and probably theoretically it's bad. But if you have many examples, it shouldn't matter as much. Stratifying is especially useful in multi-class problems. Say if you have 20 classes and some of the classes do not have many examples, and stratifying is going to be very helpful in these cases. In general, whether this is a good idea or a bad idea, these are all difficult questions, and usually they are very much context dependent.